हेलो सुरेंद्र सुरेंद्र
आपके द्वारा डायल किया गया नंबर नेटवर्क कवरेज क्षेत्र के बाहर है।
यस सर।
अरे वो मुझे स्क्रीन शेयरिंग का राइट थी।
एक सेकंड सर, अब मैं आपको पोस्ट बना रहा हूँ, देन यू विल गेट ऑल द राइट्स।
ठीक है। आप प्रतीक। हाँ मैं।
So are you getting the rights now?
आपके द्वारा डायल किया गया नंबर अभी व्यस्त है।
शुरू करें. Hi, dear participants, welcome and good afternoon to everyone. And let me say outrightly that it's a great honor and occasion for all of us that we have today with us Professor Sebastian. And I think Professor, those people who are working in India on dynamic panel, they know you by name. And in fact, they are very excited to listen to you, and they are very excited to interact with you. And hopefully we will have wonderful time interacting with you. And I extend very warm welcome to you from University of Delhi, our department. And you will glad to know that we have participants from different universities of India, different colleges of India. We have some people from Nepal, and we have one participant from Helsinki, also Finland. So very great, response we get for this, your workshop and this webinar. And I hope that every participant at the end of this webinar will get a lot of understanding about the dynamic and the command which you have put in the stata. So with this welcome remark, I call upon Pratik. So Pratik, please introduce Professor and tell something to the participants about what kind of protocol they have to follow during the workshop. Okay, Pratik. Pratik, are you there?
Yes, absolutely. Thank you so much, Professor C.P. Gupta, for opening today's proceedings. And we are indeed very delighted and privileged to have Professor Sebastian with us today for this webinar on dynamic panel models. So a very warm welcome to him, and also a very good afternoon to all the participants. So as Professor C.P. Gupta just mentioned, that many of you might actually be knowing Professor Sebastian already, but let me just introduce him formally and talk about his work. So Professor Sebastian is currently working as an assistant professor of economics at the University of Exeter, UK. And he has completed his higher studies from University of Leipzig, University of Mannheim, and Goethe University. Prior to joining the University of Exeter Business School in 2015 as a lecturer in economics, Professor Sebastian completed his doctoral studies from Goethe University at Frankfurt, Germany. His international experience includes a research visit at Michigan State University on invitation by Professor Jeffrey Woolridge, and a short-term consultancy in the Poverty Reduction and Economic Management Network of the World Bank in Washington, D.C. He can also look back to a 19-month experience in the economics department of Behrisch Landsbank in Munich after he received his economics diploma from the University of Mannheim. His research interests center on the advancement of econometric methodology with a primary focus on estimation and statistical inference in dynamic panel data models. Some of his projects also touch the areas of time series econometrics, classic instrumental variables estimation, and spatial econometrics. The development of several widely used stata packages also forms part of his work. His papers have appeared in top journals, including Oxford Bulletin of Economics and Statistics, the Stata Journal, Journal of Applied Econometrics, and Economics Letters. And in fact, while I was going through his website yesterday, I figured out that he has also received the Teaching Award for Outstanding Pastoral Care at the University of Exeter Business School recently. So a very warm welcome to you, Professor Sebastian. Lastly, I would just mention that Professor Sebastian is extremely active on Stata List, which is a forum for posting your queries related to not just econometric methodologies, but also the software Stata. He's very active on that platform. and he has answered all my queries with exceptional quickness and precision all the time. And this is where I got to know him and interact with him personally for the very first time. So thank you, Professor Sebastian, for your brilliant contribution on the Statalist platform as well. So we welcome you, and we now pass on the baton to you to begin today's session on dynamic panel models.
Just one thing before, Professor, whenever you give any response on this data list, so Pratik and we used to discuss it at length, and what sense it makes to us, it's difficult. But anyway, we are really happy that your responses were very quick and spontaneous many times. So thank you again and welcome you, and its platform is open to you. Thank you.
Thank you, Professor Gupta. Thank you, Pratik, for the very kind introduction, and of course for the invitation to give this talk today. It's a great pleasure to speak to you. And it was a great pleasure talking to you before on data list. Always kept me thinking about the several aspects of dynamic panel models and GMM estimations. That was also quite interesting for me to interact with you. But so I believe we can take questions throughout the talk. I won't be able to monitor the chat, so I hope that someone, maybe Pratik, can alert me whenever there's any question.
Absolutely, Professor Sebastian. And in fact, before you begin, just a word of instruction for all the participants. I request all of you to keep your microphone as well as your camera switched off during the entire lecture. And if you have any questions, please post them in the chat box. I'll track the questions and we'll put forth these questions to Professor Sebastian. Please go ahead, Professor.
Thank you very much, Pratik. Okay, so the topic of this webinar today is a talk on dynamic panel models, which in principle is a quite wide area. So I have to narrow it down a bit for the talk given the time we have. So I decided to focus first of all just on linear panel models. There's also a whole area of work on non-linear panel models, but that would go far beyond the talk today. Then I will also have to narrow it down on short T dynamic panel models, which means we have only a short time horizon in our data set as opposed to data sets where we have a large time horizon. If you have quite a large number of time periods in our data sets, then there are a couple of more things we can do. We can allow for much more heterogeneity in the data in our model. We can allow for various forms of cross-sectional dependence. We can allow for heterogeneous slopes. Then we would need to use different estimators. Some of the main problems that arise in short T dynamic panel models, in particular the bias resulting from the presence of the lag-dependent variable, that's less of an issue if you have large time horizons. So the methods and procedures that we need when we have short T versus long T are quite different. So here I'll just focus on short T dynamic panel models. And even in this short T context, then there are different estimation methods, how we can estimate such models, ranging from maximum likelihood estimation, bias corrected estimation, to the probably most popular approach, generalized method of moment estimation. And I will mostly focus on the last approach, generalized method of moment estimation. But at the beginning, I will also briefly talk about two alternative estimation procedures before I come to the GMM estimation. So let's get started. as you know, panel data is quite useful, given that we have both a time dimension and a cross-sectional dimension. So we observe the same individuals or firms or countries over several periods in time, which allows us to model dynamic adjustment processes and to account, at least for some, unobserved heterogeneity across units. In particular, if you have endogenous variables or such dynamic models that lead to some heterogeneity, then instrumental variables, or more generally, the generalized method of moments approach is really the predominant estimation techniques for such models, in particular when the time horizon is short. But there are also alternatives, in particular if you are willing to make some stronger assumptions, namely maximum likelihood estimation or bias corrected estimation that directly addresses the bias we have in such models. And these alternatives can be really attractive if these stronger assumptions hold. Then usually those approaches are more efficient than the instrumental variables-based approaches and also have often better finite sample properties. So this is a model, the econometric model we are looking at. We have a dependent variable, yit, and a lag-dependent variable, or possibly several lags of the dependent variable as predictor variables, plus some additional regressors that are observed. And then we have some unobserved components, which is just the idiosyncratic error term UIT. And typically in such models, we want to control for some sort of heterogeneity that we cannot observe. And we often assume, in particular in this short T context, that this heterogeneity is constant over time. So there might be persistent differences across firms, across countries, across individuals that we can't observe, but we still need to account for them because these persistent differences might be correlated with our regressors. And as a key feature in such dynamic panel models, because alpha I, these time constant unobserved effects determine the dependent variable yit, because they are time constant, they also determine the lags of the dependent variable. That means by construction, the lag dependent variable will be correlated with the unobserved effects alpha I, which creates a bias in these models, which is the fundamental issue we have to solve, in particular if the time dimension is short. So again, I'll just focus on settings with a large number of cross-sectional units, firms, countries, individuals, and just a few number of time periods. Then at the beginning of our empirical analysis, we usually have to make some assumptions. We set out the model, and part of setting out the model is making assumptions, in particular about the nature of these regressors. Are these regressors so-called strictly exogenous, which means they are uncorrelated with the errors, UITs, the idiosyncratic noise, and we can't explain for any period. And strictly exogenous in particular means that also there's no feedback from past periods, and there's no anticipation from anything that might happen in the future. While if we talk about weakly exogenous, also called predetermined regressors, then some of the past shocks that are affecting the dependent variable might also affect current outcomes of the regressors, but we don't allow for current simultaneity, current feedback from the current shocks on the regressors. While if you talk about endogenous regressors in this context, we allow for the regressors XRT to be directly correlated with the shocks UIT. So there's some immediate feedback, immediate simultaneity presence. Now, for some of you, this notation, this terminology might probably be a bit confusing because there's still this unobserved component alpha I in the error term. And we may still want to allow for these regressors X to be correlated with the unobserved heterogeneity alpha I, which in the traditional sense would mean these regressors are no longer exogenous as soon as they are correlated with the unobserved component alpha I, which is part of the overall error term. These regressors will be endogenous in the traditional sense. But, and this will be important in particular for the estimation methods we look at, this classification of regressors as strictly exogenous, weakly exogenous, endogenous, that just refers to the relationship between the regressors X and the error term UIT. And on top of that, we might still allow for the regressors X to be correlated with alpha, even if we classified them as strictly exogenous before. Now, for simplicity, we assume that the errors UIT, the idiosyncratic errors, are serially uncorrelated. That might seem a bit more restrictive than it is. In practice, if there's some serial correlation, we can often deal with it by adding more legs of the dependent variable and the regressors X to proxy for any remaining serial correlation. So that's also why sometimes it's useful to have more than just one leg of the dependent variable in our model. Okay, so now the main problem is that the leg dependent variable is endogenous because it's correlated with the unobserved component alpha I. Now, first, let's assume that all of the regressors X are strictly exogenous, so we don't have to worry about any additional endogeneity or feedback coming from the idiosyncratic error term UIT on the regressors XIT. They may still be correlated with the unobserved effects alpha I. But in any case, because the leg dependent variable is correlated with the unobserved effects alpha I, the pooled ordinary least squares estimator is biased and inconsistent because the leg dependent variable is endogenous in that sense. That same would also apply to the random effects estimator if all the regressors are uncorrelated with the alpha I's, because still the leg dependent variable would be correlated with those effects. The one approach you probably know from static models is that we just apply the fixed effects estimator that eliminates these time invariant effects, and by the way, any variables that are time invariant, by subtracting the time averages of every variable, including the error term, given that the alphas, the unobserved effects, are constant over time. Subtracting the time average means we eliminate them from the model. But now, unfortunately, while the alphas are gone, the mean deviated leg dependent variable becomes correlated with the mean deviated error term, because the average errors UI bar, the error term for UIT minus 1 is included, and UIT minus 1 directly determines the leg dependent variable YIT minus 1. So as a consequence, also the fixed effects estimator is biased and inconsistent as long as the time horizon is fixed. So as a side note, which you might know, the fixed effect estimator is also equivalent to the least squares dummy variables estimator that we get if we include a dummy variable for each of the cross-sectional units to capture these unobserved effects alpha I. Okay, now this bias is quite well understood since the work of Nickel at least. So we know how this bias looks like that we get from this estimator and this model. And knowing how this bias looks like, essentially we can devise a bias correction procedure, which is a quite attractive approach because it takes the fixed effects estimator, which is a least squares estimator, which has a really small variance, and subtracts a bias term to account for this endogeneity of the lag-dependent variable. That's the error term. Okay, so maybe let me ask Pradeep quickly. Is there any question in the chat up to this point that I may want to answer?
Yes, Professor Sebastian. So a question has come up just now. How do we determine whether a particular variable is predetermined, endogenous, or exogenous if, let us say, there is no guidance from the underlying theory?
Right. So that's a very good point. So ideally, we have an idea from economic theory that tells us whether there could be any feedback or any simultaneity that helps us to specify whether a regressor is strictly exogenous, predetermined, or endogenous. But this may not always be the case. And if that's not the case, then we may have to empirically test the underlying assumptions, which I will talk quite a bit about later in the context of the generalized method moment estimation.
Right. So Professor Sebastian, in fact, I also have a follow-up question to that. So in your previous slide, we were talking about the lag of the dependent variable being correlated with the time invariant variables, right, which are represented in a consolidated manner by UI. But I have always wondered that these time invariant variables do not vary across time, and that is why it is not logical or not rational to calculate their Pearson's coefficient of correlation with a particular variable, let's say the lag of the dependent variable, which is varying across both the dimensions, that is cross section as well as time. So now here you have a variable which is varying across both the dimensions, and then you have a variable which is varying only across one dimension. So to that extent, how do we figure out mathematically whether these two variables are correlated or not, or is it just a matter of theory?
So for the lag dependent variable, it immediately follows from the theory, because alpha I determines the dependent variable via t in any period. Therefore, it also determines directly the lag dependent variable here t minus 1. Right? Just write the same model, replace t on the left hand side with t minus 1. So you shift the time index by one period, but for alpha I, no time index gets shifted. It still remains in the equation. So alpha I also determines the lag dependent variable. That directly follows from the construction of this model. And for any other regressor, that's really a matter of the cross-sectional dimension, whether there's correlation in the cross-sectional dimension, meaning that they, for some countries, the investment is significantly higher if they have certain characteristics, like they lie in particular in a certain geographic area, Africa or Latin America, Asia. So you often have some geographical clusters which to some extent can be captured by these country-specific fixed effects, alpha I, or any other underlying characteristic that correlate with our regressors. So that's not really a correlation over time. That's really some of our units have, over the whole time period, significantly higher or lower values of the regressor than some other units. Then we would.
Okay. Right. So which means that, in order to determine whether both of these variables are correlated or not, we need to focus on the one common dimension across which both of these variables vary, and that is cross section.
That's correct.
Okay, and then is there a mathematical measure also by which we can calculate, or then again, is it on the basis of theory that we have to justify our arguments?
Well, since we can't observe these alpha i's directly in the data, we cannot simply compute the correlation. So initially, we would need to theorize about the relationship, and then in the context of the generalized method moments approach, or more generally, also, if you just look at the alpha I, we can then estimate the model under a random effects assumption or under a fixed effects assumption. Under a random effects assumption, we assume that they are uncorrelated. Under the fixed effects assumption, we assume that they're correlated, and then we might be able to use some sort of a Hausmann test where we check whether the coefficients from these different approaches are significantly different from each other. We know the fixed effect estimator, assuming we account for the bias, fixed effect estimator would always be consistent, but the random effects estimator would be more efficient if this assumption is correct. And on this ground, we could contrast the estimate from two approaches, getting some insights about whether a random effects or a fixed assumption is more appropriate. There are alternative approaches like a correlated random effect approach, sort of month-lag approach. We can check for specific regressors whether they should be treated as fixed, or whether the effect should be treated as fixed or random with regard to these regressors. So there are ways we can check for that in the context of the estimation, but not prior to the estimation, because we don't have the alpha. We cannot simply compute the correlation.
All right. Thank you, Professor Sebastian.
Mm-hmm. Okay, so let's get on then with the bias correction approach. There have been bias correction procedures proposed in the past, in particular by Jan Kiewiet. One shortcoming of his estimator is that it relies on some initial consistent estimator, and it doesn't really provide analytical standard errors. The inference can become quite cumbersome if you have to bootstrap the results, for example. So more recently, in joint work with Yuko Breitling and Katsuhiko Hayakawa, we have proposed a new bias corrected estimator that's implemented as a methods of moments estimator that takes the knowledge about the bias in the first order condition, say of the fixed effects estimator, and analytically corrects for this bias. And by the way, this estimator is also equivalent to the so-called adjusted likelihood estimator of Damon Jochmans and an earlier iterative bias corrected estimator, Bunin-Carré. What we do in our papers, we really highlight that we can implement this as a simple method of moments estimator, which directly leads to some analytical form for the standard errors. So it's quite easy to handle, and it's implemented in a new command, xd-tpd bc. We can flexibly allow, as I just said, random effects or fixed effects assumption whether the regressors are correlated or not. We could possibly contrast the two to the if the random effects assumption is justified. There's a technical shortcoming, which is that this is a non-linear estimator for the linear model, which means we can possibly have multiple solutions, and then we need to be careful in picking the right one, which fortunately can be done simply by checking some condition on the gradient. So this is quite a technical, I understand, so don't worry if this was going a bit above your head. Just wanted to briefly illustrate that there are alternative methods to GMM, like this bias corrected estimator in Stata. It's quite simple. You just need to install this command from my website and then type the dependent variables, the independent variables. And in the simplest case, that's all you need to do. And then you get the standard output with the results for the dependent variable and regressors. Don't want to interpret these results too much at this point. Let me just move on to actually closely related approach with maximum likelihood estimation, which accounts for the fact that the correlation of the lag-dependent variable with the unobserved effects essentially can be dealt with by dealing with the initial observations, the correlation with the initial observations and the unobserved effects. And one approach is that we then model the impact of these initial observations on the joint likelihood function, which requires some additional assumptions. Set up the joint likelihood functions that accounts for the whole correlation structure. And again, this would take care of the bias, assuming that all the regressors, the other regressors, are strictly exogenous. And it turns out that actually this maximum likelihood approach is quite similar to the bias correction approach, in the sense that it implicitly also does a bias correction. Again, there are fixed effects and random effects written for such a maximum likelihood estimator. And instead of just going through all of these details, let me just show you how you do it in Stata. Again, you would just simply download a command from my website, specify the dependent variable and the independent variables for the fixed effects case. That's in most cases all you need to do. And similar to the bias corrected estimation, you get the results that actually look also very similar to what we had before. All right. A general shortcoming of both the maximum likelihood estimator and the bias corrected estimator is this requirement for strict exogeneity of the regressors, which can often be quite unreasonable, and it's also a bit more difficult in the maximum likelihood context to test for it. So testing becomes much easier in the generalized method of moments framework. So before I start with the GMM approach, let's see again if there are any questions about the bias corrected estimation or the maximum likelihood estimation.
All right, so Professor Sebastian, I think we can go ahead. There aren't questions specifically with regard to the content you have just discussed. Let me just check once again. So, okay, so there was a question regarding the drawbacks of maximum likelihood estimation method vis-a-vis system GMM, because of which we usually prefer system GMM over MLE.
Right, that's a very good question. So let me start again with the advantage of maximum likelihood or bias correction for the matter, which is very similar. The advantage is that if the additional assumption of strict heterogeneity of all the regressors X is satisfied, then the maximum likelihood estimator is more efficient than the GMM estimators, and often it also has a much better finite sample performance, in the sense that any small sample biases or are smaller, and due to the efficiency, also the standard errors will be smaller, so we get much more precise estimates. There are some technical shortcomings regarding to solution findings. As I said, sometimes we have multiple solutions, but that can be in most cases dealt with. So the main shortcoming really is this requirement for strict exogeneity, and often we don't really want to make the assumption that all of our remaining regressors are strictly exogenous. We may want to allow for some feedback, so we have some predetermined regressors, or even some simultaneity, so we have some extra endogenous regressors. So that's really the main shortcoming of at least this basic maximum likelihood approach. There are some more involved maximum likelihood procedures that go into the area of structural equation modeling, where you can allow for some feedback. But then this becomes quite similar to what we also do in the GMM framework. Okay.
All right, so we can move forward, I think.
Great. So let's get started with Gmn estimation. Very briefly at the beginning, what is a Gmm estimator? What does it do? The Gmm estimator in general is based on some moment conditions that are an assumption that characterize our data generating process that tell us something about our population. For example, in the very basic linear regression model, where we have some instrumental variables, our assumption would be that these instrumental variables are uncorrelated with the error term. In other words, that the expected value of C prime E is equal to 0. So that would constitute our moment conditions. In our dynamic model, part of X would be a lag-dependent variable, but still we can look for appropriate instrumental variables, assume they are uncorrelated with the error term. So in the population, the instruments are orthogonal to the error term, which constitutes our moment conditions. Also, the bias-corrected estimator that I previously mentioned is essentially constructed as a method of moments estimator based on some moment conditions. Ignore for the moment the second component here with the blue part. Then what you get is just the fundamental moment condition for the traditional fixed effects estimator, which can also be seen as a method of moments estimator, where the mean deviations are orthogonal to the errors. Now we have seen that this is actually not the case because the lag-dependent variable, after subtracting the mean, will be correlated with the errors because this mean includes all time periods and therefore also will be correlated with the error term EIT. Therefore, we need to correct this bias, and we can compute an analytical form for this bias that we just subtract here. So the approach that we have with this bias-corrected estimator is correcting this moment condition such that once we take expectations, it holds again that the expectation of this product is equal to 0. And for this, we need this extra term, which we can then use to estimate the model. And then a method of moments estimator, or more generally a generalized method of moments estimator, minimizes the quadratic distance, a quadratic form, very much like the ordinary least squares estimator minimizes the sum of the squared residuals. Here we minimize the sum of squares of these moment functions. And if we have an over-identified model where we have more instruments than regressors, then we also need to include a weighting matrix W, which I talk about in a second. So let's first think about the case where the model is just identified. We have as many instruments as regressors. This is, for example, the case with the bias-corrected estimator. Then this weighting matrix is irrelevant, and we just need to choose these coefficients essentially such that these moment functions evaluate to 0, which minimizes the quadratic form. If these moment functions are 0, the square of the moments becomes 0 as well. And actually, this should be the average of these moment functions here. Okay, so we have a criterion functions that we are minimizing. That's what the Gmm estimator is doing. If the model is over-identified, then we need this weighting matrix because we cannot turn these moment functions is exactly equal to 0. They will always be remain positive if you have more instruments than regressors, more instruments than coefficients to estimates. Which means we need some weighting of our restrictions, our moment conditions that we impose, and this weighting is done by this weighting matrix and an optimal weighting matrix. It gives us the smallest variance, therefore the most efficient estimator, is based on the asymptotic covariance matrix of the moment functions. And typically we obtain such an estimate of the optimal weighting matrix from some initial, mostly inefficient Gmm estimator. And then in a second step, we use this estimated weighting matrix to obtain an optimal efficient estimator, which is the so-called two-step estimator that you might have heard about already. We'll see about how this works in practice with the Gmm estimator for dynamic models in a moment. So let's get back to the linear dynamic panel model. The main approach to estimating such models is to start again with removing the unobserved effects. Here we do a first difference transformation instead of within groups transformation where we subtract the mean, mainly for the purpose that we can easily allow for predetermined regressors or endogenous regressors. If we have this first difference transformation, I get back to the mean deviations at some later stage. But again, after removing the unobserved effects alpha I, now the first difference of yit minus 1 will still be correlated with the first difference of the error term, because the error term includes uit minus 1, which directly determines yit minus 1. So now we are trying to find some instruments, and assuming uit is zero uncorrelated, then we can use further lags, either first difference or in levels of the lag dependent variable as instruments for our endogenous regressor delta yit minus 1. Because if you take yit minus 2, that will be determined before the shocks uit minus 1 and uit that are part of the error term. And if there's no zero correlation in these level shocks, then yit minus 2 will be uncorrelated with our error term delta uit. Therefore, this would qualify as an instrument for delta yit minus 1, and hopefully it's also sufficiently correlated. And a similar approach we can do if some of these regressors are either predetermined or endogenous. We can just resort to lags of these regressors from sufficiently from the past that serve as instruments. So for example, if the regressors are endogenous, that means they are correlated with uit as well, then delta xit, which also contains xit minus 1, will also be correlated if uit minus 1. Therefore, similar to the lag dependent variable, the first available instruments, if we go backwards in time, would be xit minus 2, assuming that there's no anticipation effect from the future. Then xit minus 2 will be uncorrelated with both uit and uit minus 1, qualifies as an instrument. For predetermined regressors, we don't need to go that far back in time. We can directly use xit minus 1, which might be correlated with uit minus 2, uit minus 3, but it's uncorrelated with the shock uit minus 1 in the same period. That's what makes it a predetermined regressor. So this would be a valid instrument as well. And based on this classification, we can set up our moment conditions that then define our Gmm estimator. We just look at which of the past observations qualify as valid instruments, which of them are uncorrelated with the current error term in our first differenced equation. So these are the past dependent variables from t minus 2 onwards. For strictly exogenous regressors, you could use the regressors in any time period. For predetermined regressors, from t minus 2 backwards. For endogenous regressors, from period t minus 2 backwards. They would be uncorrelated. They can't change in the error term. And then, yes.
Yeah, Professor Sebastian, so there are a couple of questions. So Soumya is asking, how do we decide how many lags to be used as an instrument? Same is the question by Adya. So,
Right, so I'll come to that. The most important part for now is to understand what the first valid lag. So for the lag-dependent variables, it would be yt minus 2, but then also yt minus 3 would be valid, yt minus 4, yt minus 5. For predetermined, because it's similar, xt minus 1 would be the first valid lag. Xt minus 2, xt minus 3 would still remain valid. For the moment, let's assume we use all of the lags that are available. This may not be ideal. I'll come back to this issue in a moment.
all right. And also, Professor Sebastian, does the choice of appropriate lags to be used as instrument depend on the transformation that we are using for the regressors?
Yes.
First difference or forward orthogonal
Right.
deviation?
So I'll come back to alternative transformations that get rid of the unobserved effects, like forward orthogonal deviations, and instead set up actually will turn out all of these time indices essentially shift by ones instead of yt minus 2 as a first valid instrument. Already yt minus 1 will be a valid instrument, but I will come back to that as well.
Okay, okay. Thank you so much.
Thank you. Okay, and then we just combine all of these moment conditions that we have derived from our theoretical considerations, put them all together, and that gives us some huge instrument matrices. Here again we see for the period t equal to 2, the second leg of the dependent variable would be a valid instrument, which is y0. You can't go back further in time because we just don't have the data. For t equals 3, we would have two valid instruments, the second leg, which is yi1 and yi0. And the more we go towards the end of our data set, the more time periods become available as lags. For the last observation, we have all the observations from y0 until yt cap t minus 2 available instruments. And this gives this familiar GMM type structure as this triangular structure of the instrument matrix. And for the regressors, depending on how we classify them, that looks quite similar. So essentially we have some instruments. So we can set up our moment conditions, and then we just minimize the squared, the difference, the weighted squared difference of these moment functions. So the next step is to obtain an optimal weighting matrix so we can get efficient estimates. If we have serially uncorrelated errors in levels and homoscedasticity, so the variance is constant, then an optimal weighting matrix actually can be obtained without even estimating or without obtaining an inefficient estimator in the first step, because we know exactly how the correlation structure of our first difference errors looks like. If there's no serial correlation in levels for the UITs, then there's still some first order serial correlation in first differences, because UIT minus 1 is both part of delta UIT and delta UIT minus 1. And we can account for that analytically by constructing our weight matrix appropriately that accounts for this first order serial correlation. Okay, Now, how do we do it in Stata? There are different ways. You can use some official commands, xda_bond, xdpd, or even you can set up this model with the more flexible gmm command, even though this can become a bit cumbersome. And then there are two community contributed commands. One by David Woodman, that's out there for quite a while, and probably most of you have heard about, or maybe even used, xda_bond2, and then my xdpd gmm command that can do most of the things you can also do with xda_bond2. Both of these commands have some different advantages. Sometimes xda_bond2 can be quite a bit faster. xdpd gmm is quite a good bit more flexible. You can do a couple of things with it that you cannot do with xda_bond2. So here I'll just focus on the xdpd gmm command. And the way you would specify this first difference Gmn estimator would be you just specify the regression model, the dependent variable with its lag, and the regressors W and K. Then you specify that we are using a first difference transformation with this option model diff. And then you're specifying the instruments in the this triangular form. For the lag dependent variable, we said we need to start with the second lag. This second element in this lag option, this dot, means for now we want to use all the available lags, so the second, third, fourth, and so on, as far as available. W, we want to classify at the beginning, just as an example, as predetermined. So the first lag is the first valid instrument, and then we want to still use all the following lags. K, that's treated as a strictly exogenous regressor, so we use all the available observations, which is why I just have two dots as instruments. Now, if you do this, we get again the usual data output, but we see we have a huge number of instruments, which can become quite of a problem, as we'll talk about in a moment. And also below the command, you will get to see all of the instruments that are used. For any period, you can see which instruments are available, which instruments will be used. Before I talk about the number of instruments, let's think about what happens if the error term may be heteroscedastic. Then the one-step difference Gmm estimator is no longer the efficient one. We need to obtain an optimal weighting matrix. We get this optimal weighting matrix by initially estimating the model with this inefficient one-step estimator. Then from this one-step estimator, we obtain the residuals and use those residuals to construct an optimal weighting matrix that we then use to re-estimate the model, which gives us the efficient estimates. There's not too much you need to worry about this in practice because Stata is doing all of this for you. All you need to specify is this two-step option for the Gmn command. What it also does, if you combine it with robust standard errors, which you should typically always do, it applies a finite sample correction to the standard errors, the so-called Windmeyer finite sample correction, which is necessary because just be shown that in finite samples and small samples, the standard errors otherwise could be quite severely biased, which is a consequence of, in the first step, estimating this weighting matrix instead of knowing what the optimal weighting matrix is. But again, the command is doing all of this for you. So all we need to do is essentially to add the two-step option and to make sure that we have robust or cluster robust standard errors. Then the command automatically estimates the model in both steps and produces Windmeyer corrected WZ robust standard errors, and everything should hopefully be fine. Okay, before we move on to the too many instruments problem, any further question up to this point?
Okay, so Professor Sebastian, how do we figure out with regard to dynamic panel estimation whether the error term is heteroscedastic or not? Because I am aware of some commands which we can use when we are employing fixed effects estimator. So there is a command called xtest3, but is there any specific command to check whether the error term is heteroscedastic or not in a dynamic panel data model?
I'm not aware of any specific command. So one thing we could do, and I'll get to this later, is we can explicitly incorporate the assumption of homoscedasticity by using some sort of nonlinear moment conditions in addition to the moment conditions we already have. And then again, we can use some sort of a Hausmann test to compare the model with or without the additional moment conditions that are valid under homoscedasticity. And if the Hausmann test rejects these additional moment conditions, then this would be evidence that the homoscedasticity assumption is violated. But as a general rule for such models, it's always good to allow for some heteroscedasticity. But particularly if we are not sure about it. So just estimating, you don't really lose much by allowing for heteroscedasticity. You just have to estimate the model with a two-step estimator, and then you automatically get estimates and standard errors that are robust to heteroscedasticity. Now, having said that, in particular, if your sample size is relatively small, estimating this model with a two-step estimator might not lead to such a satisfactory performance because of this estimation step of the weighting matrix that might be imprecisely estimated. So then you might forget about all of the efficiency concerns. You can estimate the model just with the one-step estimator that may not be efficient, but efficiency is an asymptotic concept. So if the sample size is really small, that's not something we really should worry about too much. Then it might be better just to stick to the one-step estimator, even though it may not be fully efficient. It will still be consistent. That's the most important part. And the moment conditions will still be valid under heteroscedasticity. And we can still use robust standard errors even with the one-step estimator.
Okay, Professor Sebastian, thanks a lot.
Okay, great. So then let's look at the too many instruments problem. We have seen we had really a large number of instruments. So if we just follow this approach of using all available instruments, in particular if the sample size is small, so which is often the case if we have macroeconomic data or firm level data, not so much often when you have microeconomic individual level data, then often we have a very large sectoral dimension. So we don't need to worry too much about the number of instruments, but with macroeconomic models in particular, you really need to be quite careful here. Also, the number of instruments increases quickly with the number of time periods and the number of regressors. And if you have too many instruments, in particular relative to the cross-sectional sample size, the number of units, then this can really cause severe biases of the coefficient standard errors, can weaken our specification tests that we will look at in some moment. All different sorts of problems can arise. So that's really something we would like to avoid. So it's always good, particularly if our sample size is not too large, to be cautious here, to rather restrict ourselves to a small number of instruments. So now to answer, to get started with answering the questions that arose earlier, how to limit the number of instruments. One way would be just not to use all the available legs. So maybe just to use the second leg of the dependent variable and the third leg, but not anymore the fourth, fifth, and so on. This is called curtailing of the instruments. An alternative approach is so-called collapsing, where instead of this triangular structure, essentially move all of the observations in this triangular matrix to the left, combine all of them underneath each other. That gets us a much smaller dimension of this instrument weight. So essentially what it does is it creates a sum over the time period instead of looking at a moment condition or instrument separately for each time period. So it's summing up over some of these moment conditions. And we can, in practice, also combine the approaches of curtailing and collapsing, which often is a quite good idea. And that's what I do here. Instead, that's quite easy. We just add the collapse option. And then we can curtail the instruments here. I just use 3 legs for each, or 3 instruments for each of the variables. That means for the leg dependent variable, I go from leg 2 to 4. For the predetermined versus W, I go from 1 to 3. For the strictly exogenous, I go now from 0 to 2. And if you do this, you see the number of instruments really gets reduced a lot from 126 down to 9, which really shouldn't be any problem. Now, having said that, obviously this choice of collapsing and choice of the leg order is quite arbitrary. And I'm afraid I don't really have a good advice on how to choose the leg order in practice. My recommendation would be choose a leg order in advance that gives you a reasonably small number of instruments. You can use more legs if you have a large cross-sectional dimension. If you have a small cross-sectional dimension, you should really be restrictive. But don't really start playing around trying to find the best, most significant result. That's not really a very scientific approach here. Just choose one leg order in advance that gives you a reasonably small number of instruments, and then try to stick to this leg order. So often 3 or 4 legs might be sufficient. Although if you use more of those legs, say the 5th or 6th leg, often these additional legs become quite weak instruments. The further you go back in time, the weaker the correlation between those legs and the instrumented variables becomes. And we really would want to have weak instruments. The instruments are strongest the closer they are in time to the instrumented variables. That's another reason for not using too many of those legs. Okay, that's a technical aspect that I ignore. Maybe to demystify the idea of these triangular GMM type instruments or the collapsing approach, it might be quite instructive to know that if you collapse these triangular GMM type instruments, what you get is essentially just standard instruments, as you might know from any standard instrumented variables regression in a, say, cross-sectional context. While uncollapsed GMM type instruments are also not really a black box. Essentially, they are just interacted standard instruments with time dummies. So essentially, there's nothing really special about these GMM type instruments. Okay, any question about the instrument reduction?
Not really. I suppose we can move forward.
Okay, great. Now let's get to some specification tests. A key assumption we made was that the error term in levels, UIT, this idiosyncratic error term, is serially uncorrelated. Then I've already mentioned the first difference error term has a first order serial correlation because UIT minus 1 is both part of delta UIT and delta UIT minus 1. But there wouldn't be any higher order serial correlation in first difference. And that's a way we can essentially test for serial correlation here. And that's important because if we had serial correlation in the level error term UIT, that would create higher order serial correlation in the first differences, which would then invalidate, in particular, the lagged instruments for the dependent variable. So if delta UIT is correlated with delta UIT minus 2, then YIT minus 2 would no longer be exogenous because YIT minus 2 is also a function of UIT minus 2. So we need to make sure that there's no such serial correlation. And the test was constructed for such absence of higher order serial correlation in the first difference residuals by Arlan Bond, which instead you can get easily with the ESTAT serial command. But I'll talk a bit more about this when we get to the output and data. Another important specification test is the Sagan or Sagan-Hansen over-identification test. That could give us some indication about the validity of the instruments and later on also helps us to distinguish between strictly exogenous, endogenous, and predetermined regressors. So in just identified models, we cannot really test the validity of the instruments because no matter what we do, these average moment functions will always be exactly equal to 0, no matter whether the instruments are valid or not. In over-identified models, we can actually test whether the average moment functions that are not exactly equal to 0, whether they are close enough to 0. And that's the approach of the Sagan-Hansen test, would evaluate whether this criterion function is close enough to 0. In other words, significantly different from 0. If it is, then this would be an indication that some of our instruments, if it is different from 0 significantly, this would be an indication that some of our instruments might be invalid. Okay, so the Sagan test is just after the one-step estimation, the test with the weighting matrix under homoscedasticity, and this is really only valid if the errors are indeed not serially correlated and homoscedastic. The extension is the Hansen test that we can use after the two-step estimator that uses a valid weighting matrix, no matter whether the errors are homoscedastic or not. And an extension would actually be that we could also iterate our weighting matrix estimation one step further. So instead of using the residuals from the one-step estimation to form our weighting matrix as we have done for the two-step Gmm estimation, we could also construct a weighting matrix now for this test that's based on our two-step estimate. So we re-estimate our weighting matrix that would give us an equivalent Hansen test statistic, and XDDBT Gmm is essentially showing both of these tests. Okay, let's just move on here and directly jump into the data output. So the error-bond serial correlation test we just get with the ESTAT serial post-estimation command after we run the estimation. And this shows test for serial correlation of order 1, order 2, and if you specify higher order correlations, then also here for third order correlation. And what we don't want higher order serial correlation. So here we see the second order and third order tests clearly reject the null hypothesis, which is exactly what we want. But importantly, we should also look at the first order serial correlation test. Now remember, I said the error term inverse differences by construction has a first order serial correlation if the levels error term is serially uncorrelated. So actually, we want to see that this first order test rejects the null hypothesis. This first test should reject the null hypothesis as it does here. If it doesn't, then this might be an indication of a severe problem, like having a very strong serial correlation in levels close to a unit root process, which would then become a serially uncorrelated process in first differences, but having a unit root in our error term clearly isn't what we want. This would indicate a severe model misspecification issue. So we should also check the first order serial correlation test. And then for the Sagan-Hansen over-identification test, we have the null hypothesis that the model is correctly specified, so we don't want to reject the null hypothesis. And here in this case, actually, the results are not too satisfying. Of course, at a 5% significance level, you would not reject the null hypothesis with this first statistic. The second statistic is when we re-estimate the weighting matrix one more time, we would actually reject the null hypothesis. But even in practice, we shouldn't focus too much on specific significance levels. We should get more, should be a bit more cautious in general. So probably we should look out for higher p-values to be on the safe side, because making a mistake here could be quite costly, as we would then end up with a misspecified model, potentially invalid instruments. Okay, let me skip this part and directly move on to system Gmn estimation. And let's see again if there's maybe some question about the over-identification or serial correlation test before.
Yeah, so Professor Sebastian, there is a question that which is more damaging for the quality of our beta coefficients? Is it over identification, or is it the use of weak instruments?
So in the first place, we need to make sure that the instruments are strong enough. If we have weak instruments, or if the model is generally under-identified, I will come to under-identification in a moment, then eventually the over-identification tests are of not much use. So in the first place, we need to make sure that the model, that the coefficients are identified, that we have at least sufficiently many strong instruments. And then moving on to over-identification, clearly if we add more over-identifying restrictions, more instruments, if these instruments are potentially weak, then they don't really help us in the estimation, but they can actually weaken, again, the over-identification tests or the estimation of the weighting matrix, which could lead to some poor finite sample performance of the two-step estimator, which is related to the issue of too many instruments. So we don't really want to have too many instruments. We don't really want to have weak instruments either. So in principle, it's good to avoid them and therefore often it's a good idea to curtail the number of instruments, the number of legs in the construction of the estimator. Unless we really have a very large sample size, then we can be a bit more lenient about the choice of the instruments, the number of instruments.
Okay, Professor, I think we can move forward.
Okay. Now, the system Gmm estimator actually comes into play based on one concern about weak identification. Namely that in particular, if the dependent variable is quite persistent, in other words, if the true value of the autoregressive coefficient gets close to 1, then the first differences, or then the lagged values, the instruments of the dependent variable become quite weak instruments for the first difference lag dependent variable. So it becomes very difficult to identify the autoregressive coefficient up to the point where the estimator essentially becomes entirely unreliable. And to overcome this, Blonder and Bond have made an additional assumption that gives rise to additional instruments that are hopefully strong enough to overcome this problem. And this additional assumption is essentially an initial conditions assumption that assumes that the initial change of the dependent variable is uncorrelated with the unobserved effects alpha I, which is essentially a mean stationarity assumption that you can think about, for example, in a macroeconomic context, is actually often violated if you have different countries at different stages of their development. So if delta y, the change in the dependent variable, say, is the growth rate of GDP, for example, then if countries at an earlier development stage experience very high growth rates, while countries at a later development stage experience typically lower growth rates, and this development stage that's essentially characterized by differences in these unobserved country-specific effects, then this mean stationarity assumption, or this initial conditions assumption, is typically violated. So the initial change, the initial growth rate in some set of countries then is systematically different than in another set of countries. So that's something to keep in mind from a theoretical perspective. If there's such significant or substantial differences across our cross-sectional units, then often this additional assumption for the Blonder-Bond system Gmm estimator is actually quite often violated. Now let's assume it's not violated. We can make this additional assumption. And a similar assumption also for the regressors xt, then this would give rise to additional moment conditions. Because then we can also assume that these changes would be valid instruments for the model in levels. Unlike before, where we had levels, like levels as instruments for the model in first differences, now we use like changes as instruments for the model in levels. For the dependent variable, that would be the first leg. For the strictly exogenous or predetermined regressors, we can use the contemporaneous changes. For endogenous regressors, because xit is correlated with uit, therefore also delta xit is correlated with uit, we again need to use the first leg. Here, I just specify one leg. I don't specify additional legs because typically, at least if we use all the available legs for the first difference model, then using additional legs in levels would become redundant. Therefore, we typically just use a single instrument for each variable for this level model. Again, we stack all of these moment conditions together and combine them with the previous moment conditions for the model in first differences. For the level model, for example, for y, for the dependent variable, we get again such a triangular Gmm types matrix. For the second period, if delta y1 as an instrument, for the third period, delta yi2, and so on. And we can also collapse these instruments again to conserve on the number of instruments, which would mean just summing up over all of the columns, moving all of these instruments into a single column. And similarly, also for the regressors X. And now very briefly, a technical aspect. Well, it often feels like a black box to think about. Well, we have this first difference model, then we have this instrument for the level model. Now we combine them somehow, and it's often hard to imagine how this works, combining these different models. What actually turns out is that the first difference transformation is essentially just applying some transformation matrix D to the error term U, which wipes out all of the unobserved effects alpha. So applying this transformation matrix to U is the same as applying the transformation matrix to the combined term of alpha plus U, which was E. And then instead of applying this transformation matrix to the directly to the equation, to the errors in our equation, we can, so instead of forming D times E, we can also apply it in the other direction to essentially transform our instruments that we constructed for the first difference model. So instead of forming D times E, we form C prime D. And that gives us some new transformed instruments, called them C tilde, for the level model. So essentially, we can think about this as just having instruments only for the level model, which would then just be a standard instrumental variable GMM approach, nothing very special about it. And now these transformed instruments, these are not so intuitive how they look like. Therefore, it's still a good idea to think about it in the context of the transformed model, but that's really just a device to motivate the construction of the instruments, because we know what are valid instruments in our first difference model. But from an estimation perspective, actually we don't estimate the model in first differences. We just construct some sort of instrument C tilde that are motivated from our first difference model. And eventually, from the perspective of estimations, these are all just instruments for the level model. And the instruments C tilde are just constructed in a way that they are uncorrelated with the unobserved effects alpha. And that's also how XTDBD GMM is internally implemented. So we need to think about an optimal weighting matrix again. Let's leave aside these technicalities here. So essentially, we just construct again a two-step estimator where we get some consistent estimates from the first step to then form the optimal weighting matrix. In practice, there are different candidates now for the initial weighting matrix. They all lead to slightly different estimation results. All of them are valid. It's not clearly clear a priori which one is best. I'll talk a bit more about the how to avoid the arbitrariness of the choice of the initial weighting matrix in a moment. So essentially, they differ in the way how they take into account the correlation of the first difference errors. This last one wouldn't take that into account. This second one would take into account the correlation of the first difference errors for the first difference model, but then would ignore that there's also some correlation between the first difference errors and the level errors, which is taken into account by this first weighting matrix, but it's still not fully accounting for the covariance structure of the error term, because it essentially ignores the unobserved effects in constructing the weighting matrix. So in that sense, it's not necessarily clear which weighting matrix is to be preferred. Again, in Stata, you can estimate the system GMM with official commands. The GMM command now looks really complicated with the XT812 command or with the XTDBD GMM command, which I will continue to focus on. And for get your questions, all we have to do in Stata is you need to add these additional instruments for the level model, which we do by specifying again this GMM option. For the dependent variable, I want to use the first leg and the first leg only, which is why the leg option ranges from 1 to 1. I want to first difference the leg dependent variable. Remember, we use differences as instruments for the level model and levels as instruments for the first difference model. So this difference here is not to be confused with model difference. Model difference specifies for those instruments we use instruments for the first difference model. Now this difference option is the same as the first difference operator. It transforms the instrument, not the model. And we specify instruments for the level model. For the predetermined and strictly exogenous regressor, we can use contemporaneous legs, leg 0. And for system GMM to get efficient estimates, now there's no way around the two-step estimator with the robust variance covariance estimate. But again, in some cases, in particular, the sample size is very small, we might still want to resort to the inefficient one-step estimator, just to avoid some problems of poor estimation of the weighting matrix. And then again, we can run our usual specification test. Okay, before I move on, let's see if there are any questions.
Right. So, Professor Sebastian, Shrimoy is asking that let's say if the number of instruments exceed the number of groups while running dynamic panel estimation, then what do we do? Is there any solution to this problem?
So the number of instruments should ideally be much smaller number. Even if it's below the number of groups but gets close to it, that's usually a too large number of instruments to get reliable estimates. We really run into problems of biased coefficients, biased standard errors, biased or unreliable specification tests. So we really should worry about getting this number of instruments down. And the way to do it is collapsing of instruments and curtailing of the instruments, not to use a large number of them. That's really what we need to do here.
Right. And there was another question in the chat box. Yukti was asking that is there any threshold to divide your sample as being large or small on the basis of T?
So there's no fixed threshold. I don't really want to name any specific number here that's then used later on. But say if you, so sometimes I see people asking questions on Stata list who just have 20, 30 cross-sectional units, and with that few observations, that few cross-sectional units, running a sophisticated Gmm estimation really is not very promising. We can't really rely much on those results. We maybe just want to resort to a very basic instrumental variable estimation, no over-identifying restrictions. But on the other side, if you have 100, 200, or in microeconomic data, that's 1,000 cross-sectional units, then there's not much to say about.
All right, so I think that's all for now. We can move ahead.
Let's ignore this technical aspect. Okay, so I've talked about the instruments that we can actually treat all of the instruments as instruments for the level model, which in data is quite handy because then we can actually also use the XCTBD Gmm command to generate those instruments, and then we do some further analysis with these instruments in some other commands. So for example, after the Gmm estimation, we could actually generate all of the instruments as new variables with the predict command using the IV option. And then these generated instruments, you could, for example, plug into the official IV request command. And then with the Gmm option and specific weighting matrix, you can exactly replicate the results from the Gmm, from the XCTBD Gmm command. So you may not remember the exact numbers, but these are the exact same results that we got before, with some instruments called IV1 to IV12 that came out of the XCTBD Gmm procedure. So you could even look in the data browser how these instruments look like. And essentially that's just specifying these instruments as you see for the level equation, even though some of these instruments we motivated for the first difference model. The same we could do with the community contributed IVREC2 command that could be quite useful, for example, because this IVREC2 command provides some additional test statistics that we might be interested in. Now coming to the weak identification or under identification again, aside from testing for over identification, it's really a good approach to also test for under identification first. Because if the model is under identified, then there's actually not even much use of doing any over identification checks. We first need to make sure that we have instruments that are strong enough to identify all of our coefficients. And these under identification tests are essentially rank tests that check whether the correlation matrix between the instruments and the regressors is of full rank. The null hypothesis is that it doesn't have full rank. The alternative hypothesis is that it has full rank. So essentially here we want to reject the null hypothesis with these tests. As the technical aspects, actually, this might be a bit confusing. Windmeyer has shown that under identification tests can actually just be implemented as over identification tests in some auxiliary model. Let's not get confused here. We don't really need to know that. And we can also actually check for under identification of the whole model or separately for any of our regressors, coefficients of the regressors. We can't directly do it with the XCTBD Gmm command, but luckily Mark Schaffer and Frank Windmeyer have developed a command called underID that just works like a post-estimation command for XCTBD Gmm. So we estimate the model by XCTBD Gmm, and after that, we run the underID command. It also produces over-identification statistics. So if you compare with the previous results, actually, that would be exactly the same as with the ESTAT OID command. And then it also produces what's more interesting here, the under-identification test. And in this case here, the under-identification test rejects the null hypothesis, which is exactly what we wanted to do. So here we can be quite confident that our instruments are all strong enough for the model to be identified. And what with this SW, Sanders and Windmeyer option, we can get separate under-identification statistics for each of our requesters. So if there's a problem with under-identification, these separate statistics here might indicate for which variable the problem might be, and then we may have to think about shall we maybe specify instead of a variable as endogenous, shall we maybe specify it as predetermined or maybe strictly exogenous to deal with the under-identification issue? Or do we need to look for some outside instruments? Should we go for blunted bond estimation if you haven't done so already to solve some under-identification concerns? Okay. From under-identification, we can now come back to over-identification, assuming that the under-identification is not a concern. And this now becomes quite relevant when we want to decide whether a variable is strictly exogenous, predetermined, or endogenous. Instead of just testing all of the over-identifying restrictions at once, we can look at specific subsets of the instruments that we would like to test. And we can do this by essentially comparing two models. One model where we include the instruments under investigation, one model where we don't include those instruments. And then we compare the estimates from these two models. If there's a significant difference, then this would indicate that the additional instruments are invalid. If the additional instruments are valid, then we shouldn't find a significant difference between these two models, and then the model with the additional instruments would be a more efficient one. And a way to test it is with so-called incremental over-identification tests or difference Sagan and Hansen tests, where we look at the difference of two over-identification tests from these two models. And we can do this as well with the XTTBD-GMM command. Estimate the first model, say here, just with the instruments for the first difference equation, store the results, and then estimate the same model where we add the additional bundle and bond type instruments for the level equation. So we have a system Gmm estimator. And then we contrast the two estimates with the ESTAT over-ID command, where we specify that we want to contrast this last estimation with the one stored under the name diff. And the Sagan Hansen difference test would, in this case, now reject the null hypothesis that the additional moment conditions, the additional instruments, are valid. So here we would have evidence that the additional level instruments are not valid. Now, in finite samples, this test statistic from this difference test sometimes could become negative, and then it's not really of any use. So an alternative that guarantees for this test statistic, this difference, to be non-negative is to make it, to construct it based on the same underlying weighting matrix from the full model. And this can be also done with the XTTBD-GMM command. So we don't explicitly separately specify the two models. We just run the estimate command once, and we add the over-ID option. What the command then does is it fits all of the reduced models where once at a time it leaves out one set of instruments that we have specified here, one of the GMM options is left out at a time, and all of these reduced models are fitted. And eventually, with the ESTAT overID command with the option difference, we can then get a table that shows us the difference in Hansen tests for all of these models where we leave out one set of instruments at a time. Now in this table, there's the first column, sorry, the first row, one model diff, that corresponds to what you see after the estimation commands, the instruments for the first difference model, the second leg, third leg, and fourth leg of the dependent variable. These are tested in the column difference. Now, what's important here, if we look at this difference in Hansen test, the first row, for example, looks like we can not reject the null hypothesis. The instruments appear to be valid, but actually, this difference in Hansen test itself isn't reliable, because it would only be reliable if the over-identification test for the model that excludes these instruments under investigation, so essentially the baseline model, if the over-identification test is already passed for this baseline model, which it isn't here in the first row. The p-value is smaller than the 0.5, so we would check already the baseline model, and then comparing an extended model to a model that we already rejected doesn't make much sense. So you would possibly compare a misspecified model with another misspecified model. But for the last column, if we look at all of the level instruments jointly, leaving them out, therefore just having a difference Gmm estimator. Just having a difference Gmm estimator, the over-identification test would be passed. That's the excluding test here. And then we can compare the system Gmm estimator, the additional instruments for the modern levels, with the difference Gmm estimator. That's the difference test in the last row doing. And here again, as we've seen before, we would probably reject the null hypothesis that the additional instruments are valid. Okay, maybe I take another break here and leave some room for comments and questions.
All right, so no questions with regard to the content discussed so far.
Okay, great. Then, as I get tight with the time, instead of the two-step estimator, given that I mentioned the arbitrariness of the choice of the initial weighting matrix, to avoid this arbitrariness, we might also use an iterated Gmm estimator that doesn't just re-estimate the model once, but many times until we get stable estimates, so until the estimates don't change anymore. And we can do this in Stata by just adding the option IGMM. And then we see, essentially, we have not a two-step estimator here anymore, but a 17-step estimator, where each time we re-estimate the weighting matrix, then we estimate the model, we estimate the weighting matrix, we estimate the model. And the advantage of this is that the estimates eventually don't depend anymore on the choice of our initial weighting matrix. While if you look at the two-step estimator, depending on which initial weighting matrix you choose, you get different estimates. And that's really to some extent arbitrary, because there's not too much that tells us which of these weighting matrices is the correct one. So the iterated Gmm estimator avoids this problem, because eventually it will get the same estimates no matter how you initially choose the weighting matrix. Another approach would be to use a continuously updating Gmm estimator that estimates the weighting matrix jointly with the coefficients, so not in an iterative way, but at the same time. That's not yet implemented in XGTPD GMM, but you can do it with the IVREC2 command. As you have seen before, you get the instruments from XGTPD GMM, plug them into the IVREC2 command, specify the continuously updating estimator CUE option, and then you get this DoE estimator with the same instruments that you would use in the XGTPD GMM. Now moving to nonlinear moment conditions. That's in particular a good alternative to the system GMM estimator if we don't want to make this additional initial observations or mean stationarity assumption, particularly often in macroeconomic context where this may not be justified. We already made the assumption that the errors are serially correlated. But besides using this assumption to justify the instruments, we didn't really exploit the serial uncorrelatedness of the errors. And we can do this by using additional nonlinear moment conditions. They're nonlinear because we have a product of the error U with the change in the error here. So we get some quadratic terms in the errors and therefore in the coefficients. So if the error term U is serially uncorrelated, then UIT is uncorrelated with all of the past changes of the errors. And that's something we can exploit in the estimation. And these moment conditions are valid even when the system GMM, the bundle and bond assumption is violated. And this could help us to actually also identify the coefficients even under highly persistent processes where the difference GMM estimator might have some trouble. And it also helps to improve the efficiency. Now the command needs to numerically optimize because of the nonlinearities, but that's not too much of a concern. And as a user, you won't really notice much of it. So all you need to do is you specify this option NL no serial. You get an additional nonlinear moment condition. And that's essentially it. You don't really have to make an additional assumption here. So in a sense, that's some free lunch once we have made the assumption initially that the errors are serially uncorrelated to justify the instruments for the lag-dependent variable. We can immediately use also the additional non-linear moment condition. If the errors are homoscedastic, that would allow us to use another nonlinear moment condition, because if you look at all of the squares, the squared errors, which essentially, once we take expectation, becomes the variances, and then look at differences of them. If the variance is constant, then the difference should be zero. That's essentially what's behind this moment condition. It also implies some additional linear moment condition. Let's not worry too much about that. So essentially, we can utilize the homoscedasticity assumption to get even more efficient estimates with the option NLIID. And that's what I mentioned before. We can then test this homoscedasticity assumption by contrasting the model just with the nonlinear moment conditions under absence of serial correlation with the nonlinear moment conditions that additionally assume the homoscedasticity, which we can do with a generalized Hausmann test, which actually works quite similar to a incremental Sagan Hansen over-identification test. So the underlying idea is the same. It just specifies the NLIID option. It adds a nonlinear condition and an additional linear moment condition. And then we store the estimation results. That's here we estimate the model with the no serial option. Then we contrast the two with the post-estimation command E_Hausmann. The null hypothesis is that the results are not significantly different. In other words, the homoscedasticity assumption is justified. Here we reject the null hypothesis. So we would reject the additional over-identifying restriction coming from the homoscedasticity assumption. Okay, any more questions before I move on? And maybe let's quickly talk about an alternative transformation, which is a forward orthogonal transformation, which subtracts the mean of all the future observations instead of creating first differences. Again, this would help us to get rid of the unobserved effects. But since we just remove the mean of all the future observations, now the first leg of the dependent variable already becomes a valid instrument, not just the second leg, like in the first differences where UIT -1 entered the error term. Here it's just all the future errors. Essentially, all the available legs shift up by one period for predetermined regressors. Already the current observation is a valid instrument for endogenous regressors. The first leg instead of the second leg when we had first differences. What constructs the moment conditions in the usual way. And maybe what's not known that well is that actually if you use all of the available instruments, so you don't curtail and you don't collapse, then estimating the model in first differences or with forward orthogonal deviations gives you identical results. So the two approaches are absolutely equivalent. When it's useful, in particular, to use the forward orthogonal deviations, the main situation when this is useful is when we have unbalanced parallel data with some gaps in between, because these gaps would lead to quite some data loss if we use the first difference transformation, while we can avoid this data loss with the forward orthogonal deviations. So that's one of the main situations where forward orthogonal deviations dominate the first difference transformations. Otherwise, there's often not much of a difference, or in this case, when we use all legs, they are actually exactly equivalent. Okay, any question here?
Professor Aranya had raised hand.
Okay.
Sorry, that was just by mistake. Please
Okay, no
carry
worries.
on. It's all quite clear. Thank you.
Thank you, no worries. Okay, I'll skip this part with double filter estimation. As a general rule, you almost always want to include time effects in your GMM estimation to account for some common shocks that occur at a given time. So it's the same way, like you want to allow for some time constant effects. You also want some effects that want to allow for some effects that affect all of the units in the same time. You can easily test whether this is necessary, include all of the time dummies, make a joint significance test. If they really are all highly insignificant, then you can exclude the time dummies. But as a default, I would always include time dummies. And my recommendation is to include these time dummies for the level model. There's really no use to include them both in the first difference and in the level model. If you have a balanced panel, then actually using either of the two is equivalent. So using both would mean one set would be redundant. but even in unbalanced panels, it's usually sufficient to just specify them for the level model. And XTTBT GMM makes it easy for you. Just specify the T effects option, then you don't need to worry about which dummies do I need to include, how to instrument them. The command just does it for you. Time invariant regressors, we can usually you don't need to worry about them. We can just combine them with the unobserved effects, which are also time invariant, and ignore them. But if we really want to estimate the coefficients of these time invariant effects, we need to find instruments for the untransformed level model. We cannot identify those coefficients in the transformed model with differences or forward orthogonal deviations. We need to find strong enough instruments for the level model, which often means we just need to assume that those time invariant regressors are uncorrelated with the alpha i's. We cannot just use the bonded bond instruments from before. If you assume those first differences are uncorrelated with the alpha i's, then it's hard to assume that at the same time they are sufficiently correlated with the time invariant regressors. So really we need to find specific instruments for these time invariant variables. But if we have those, we can also estimate their coefficients. You can allow for a small sample adjustment. And finally, I'd like to briefly talk about deviations from within group means as another model transformation, which is essentially what the fixed effects estimator does. Fixed effects estimator transforms the model into deviations from its means. This only works if the regressors are strictly exogenous, but in my view, it's actually the optimal way to deal with strictly exogenous regressors. So you would essentially maximize the correlation of the instrument with the regressor. It's the most natural way coming from the fixed effects idea in static models. Just do the same in dynamic models for strictly exogenous regressors. Instrument them by themselves for the model in mean deviations. And you can actually combine as many model transformations as you wish. You can combine forward orthogonal deviations with instruments for the model in mean deviations, with instruments for the model in levels. You could even add instruments for first differences, but usually you would either choose first differences or forward orthogonal deviations. There's no limit to this. And to show you quickly how this works, you could also use the GMM command here to estimate a static model. And if you specify the mean deviation option, you need to specify some no rescale sub option. Let's not worry about this. But if you do this, then you actually get identical results to the standard fixed effects estimator with XT break. So that's the idea of the mean deviations, which could be quite handy for variables that are strictly exogenous. And I think given that the time that was set in advance is basically up, let's see for the moment if there are any questions, and everything else is just bonus.
Yeah, so Professor Sebastian, regarding the forward orthogonal deviation transformation, I was wondering that when you mention it is to be used in cases where our data set is suffering from gaps, then do you actually imply that out of the entire period of time that we are studying, there should actually be some years which are missing altogether? So for example, if I am working on a time period from let us say 2001 till 2020, then by gaps, do you mean that there are several years which are missing altogether for all the cross-section units?
They might be missing for all the units. That would be one case. Or even if there's data missing in between for just some units. So for a unit, you have data from 2000 to 2005, and then again from 2008 to 2010, but you don't observe for this particular unit the data for 2006 and 2007. Even if it's just for one unit already, the forward orthogonal deviations would be beneficial.
Right. So which means that if there is a missing observation for even, let's say, a single cross-section unit, even for a single year, then forward orthogonal deviation shall be preferred to difference transformation.
In principle, that's the case, yeah. Unless the missing observations are just at the beginning or at the end, then it doesn't make a difference. But if the missing observation is somewhere in between, then the forward orthogonal deviations are usually preferred to the first difference.
Okay, so then let's say I have a completely balanced panel dataset which does not have any missing observation whatsoever, and I run, let's say, my model using both FODV and first difference. Then will the results be completely identical?
If you use all of the available instruments, so no curtailing and no collapsing, then the results should be exactly identical. If you do some collapsing or some curtailing, then the results will be different, but it's not really clear that one or the other are preferred.
Okay, okay. Thanks, Professor Sebastian, thanks.
Mm-hmm. Okay, is there any other question?
Yeah, so there was a question earlier. So Aishwarya was asking that, while running the Hansen test after estimating our model using XTDPD GMM, so basically we get two results, one pertaining to the two-step weighting matrix, another one pertaining to the three-step weighting matrix. Yes. So which one should ideally be preferred while reporting our results in research papers? Right, so that's a good comment.
Usually people just look at the traditional two-step result where the weighting matrix is the same that was used for the two-step estimation, so not iterated any further. Asymptotically, the two tests are absolutely equivalent, so it doesn't make a difference. If you observe a substantial difference between these two over-identification tests in your estimation, then this is usually a signal that there might be some problem with the estimation of the weighting matrix. So it's not really about reporting this additional over-identification test in the paper. That's really just for you to give you an idea that there might be a problem with the estimation if these tests are really quite different, which they shouldn't. So in that sense, you might think about doing the iterated Cmm estimation, where you avoid the problem of the dependence of the result on the weighting, on the initial weighting matrix. So eventually, the test will just converge also to be identical. Or if there's really an underlying issue with the estimation of the weighting matrix, a difference of these two tests could also indicate you might have a weak instruments problem or a too many instruments problem. So you maybe should rethink about how to choose the instruments, whether you should curtail them a bit more if these tests are very different. So that's really just an indication for you whether there's a problem or not.
Okay. I think we can go ahead.
Okay, so I don't know what the time frame is. I mean, initially this is at 2 hours. So what's the plan?
I think we can go ahead. You have full freedom to complete your presentation in as much time as you want.
Okay. Then let's see what else I have. I gave you the main ingredients, the main theory and how to deal with things in practice about GMM estimation. The common question is always, how do I specify the model in practice? Ideally, as I said at the beginning, you should have a good economic theory that tells us this is how the model looks like, this is how we classify our regressors as predetermined, endogenous, exogenous. And then you just estimate the model and see what you get. But often it's not that clear. You might have to deal with serial correlation, add some additional lags of the dependent variable or the regressors. The theory may not tell us immediately whether the variables should be treated as endogenous or predetermined or strictly exogenous. It's not so clear maybe whether to add certain variables to the model or not, whether to use interaction effects to account for some of the heterogeneity of the effects, and so on. So we might want to let the data speak a bit on this issue. And what can be quite helpful in this model selection process are so-called model and moment selection criteria. These are actually very similar to what you might know from a time series context, for example, the archaic or Bayesian information criteria that you can use to compare models, which essentially look at the fit of the model and add a penalty term for adding more coefficients. Here, you would look at essentially the over-identification test statistic and subtract a bonus term, which is just a penalty term with opposite sign, from this test statistic for having fewer coefficients. The fewer coefficients we have, the more efficient we can estimate them for a given number of moment conditions, or alternatively, it rewards us with some bonus if we, for a given number of coefficients, can include more over-identifying restrictions. So asymptotically, having more instruments, more over-identifying restrictions is beneficial in terms of efficiency, but just keep in mind in finite samples in particular, we need to worry a bit about the finite sample problems of too many instruments. So in essence, these model and moment selection criteria are quite similar to these familiar, say, archaic model selection criteria. So suppose we compare two models. One model where we add as regressors an additional lag of our regressors W and K compared to the model where it did not include this lag. And all of the moment conditions, all of the instruments stayed just exactly the same. We store the results from the model with the lags. And then after the second model, we use the estat MMSC post-estimation command, specifies that we want to compare the last results to those with the extra lags named xlags. And then we get a table giving us these model selection criteria for the two models, the xlags model, and the dot just refers to the previous model. And similar to the conventional archaic or Bayesian information criterion, we choose the model with the smaller value, which is the last model that we just estimated. -11 is smaller than -9, and for the other criteria, the ranking is the same. So here, adding the additional lags doesn't seem beneficial based on these criteria. And then we can use all of these criteria in some structured model selection process. The idea of this selection process, as proposed by Jan Kiewiet in a recent paper, is to remove the arbitrariness of the model selection process. It's not really a good idea to just play around with the specification, try a specification here, try one there, and just to pick the model that we like most at the end. That's really more or less p-hacking, not very scientific approach to choosing a model. You don't really want the results or the specification be guided by what we hope to get at the end. We really want to let the data speak. So we need some more structure in our model selection process. So the first step would be to specify what then Kibit calls a maintained statistical model. That should be a quite general model with as few assumptions as possible, as few restrictions as possible. So we might just treat all of the variables as endogenous. We should include time dummies, sufficiently many legs of the variables, to have a quite general model. And let's first see whether this general model passes our basic specification test, and then we can compare more restrictive models later on to this quite general model to see whether we can impose some additional assumptions that help us to get some more efficient estimates. Okay, keep in mind, if you have small samples, we still want to collapse or curtail the instruments to avoid problems of too many instruments or weak instruments. Forget about this rule of thumb here, just make sure, particularly for small samples, just keep the instruments really small relative to the number of cross-sectional observations. So just be on the safe side. Then you estimate the model with the two-step Gmm estimator, apply the windmill correction. If really you have a very small sample, maybe forget about the efficiency argument, just stick to the one-step estimator. Consistency is more important than efficiency. Then we do our basic specification tests, here, correlation tests, over-identification tests, anti-identification tests. If there's any problem with these specification tests, then we need to rethink our initial maintained statistical model. So here I used 3 legs of all of the variables. I use the forward orthogonal deviations, collapse the instruments, and here I decided not to do any curtailing. Collapsing just helped me already to bring down the instruments sufficiently. And I had time effects with the two-step estimator with robust standard errors. Okay, so you see there are not too many instruments. The serial correlation test is passed. Remember, we want to reject the first order test. We don't want to reject the second or third order test. The over-identification test is passed. Again, these two versions of the test, as I just said, they are asymptotically equivalent. A substantial difference between them might indicate a potential problem with the estimation of the weighting matrix. Here, maybe you don't need to worry too much. Both of them clearly reject the null hypothesis. And then we also check the incremental over-identification test for the different set of instruments. Remember, first, all of the tests, the baseline tests excluding a specific set of instruments need to be passed. That seems to be the case here, even though some of those p-values become quite small. But then the difference tests really don't give any reason for concern. So far it looks like the model is a good starting point. And from there, we can now work on getting more efficient estimates. So we have a model that gives us consistent estimates. That seems to be a valid specification. Everything else we do from now on is to get better estimates, more efficient estimates, more precise estimates. So we can try to reduce the dimensionality of the model by throwing out some variables that are highly insignificant. We move some of the lagged regressors if they are highly insignificant. We do it one variable at a time to make sure that we don't remove too many of the regressors. And we also keep an eye on our specification tests. Eventually, we can use the model and moment selection criteria to choose between the different models we are going to estimate now. So in the first case, let's pick the third leg of the regressor K. I haven't shown you, but in the initial specifications, this one had the highest p-value. It's clearly statistically insignificant, so we can decide to remove it from the model. Instead of 3 legs of K, I just use 2 legs now. I go through all of the specification tests, they still look all fine. Then I do the same with the third leg of the dependent variable. Again, there's no evidence to keep it in the model and remove it. Specification tests are all fine. Do the same then with the next highest with the coefficient with the next highest p-value, which now is the second leg of K. Again, after removing it, still the model passes the relevant tests. Do it with the third leg of W. Model still passes the test. So we are narrowing down our specification, getting rid of some coefficients that we don't need to get more efficient estimates. Also, the first leg of K doesn't seem to be really relevant. Specification tests are still fine. And eventually, we may even want to add some interaction effects to allow for some heterogeneity. I could have done this already at the very beginning, before narrowing down the model specification, but I didn't want to start with too complex, with a too large model, because if you have too many coefficients in the model, then we might just overfit the model. We might have too many coefficients to get reasonably precise estimates, and that's also something we'd like to avoid. But now that we have narrowed down the model a bit, we might be willing to check for some interaction effects. The first one is just a squared effect of W, and then we have some interaction effect between W and K. I treated both of them as endogenous. So we should also treat the interaction effects. If W and K are treated endogenous, we should also treat the interaction effects as endogenous and add appropriate instruments. We check the specification tests again, they still look fine. Then we can check for the time effects. Here, it looks like the time effects are jointly highly statistically significant, so we might actually be able to remove them. So in the next specification, I remove the T effects option, no more time effects. The specification tests still look fine. But eventually, if I contrast all of the different models that I just looked at, model 1 was just a large initial model, model 2 where I excluded the third leg of K, and then 3, 4, 5 where I excluded more and more of those legs. Model 7 was the model where I added interaction effects, and the last model with the dot was then the model where I removed the time effects. So even though the time effects were all statistically insignificant, actually the model and moment selection criteria tell us maybe better leave them in. The lowest values for these model and moment selection criteria are for the model with interaction effects and with time effects. Once we remove the time effects, the moment selection criteria become larger, smaller in absolute value. So this would not support the specification without the time dummies. Okay, any question up to this point?
No questions, Professor. Just a piece of advice from your side, if a beginner wants to learn dynamic panel estimation, so is there a good textbook or reading or a research paper that he or she can look at?
There's some basic covering of dynamic panel models in textbooks, even though these are already typically some advanced textbooks, more targeted towards students at the master level than at an undergraduate level, like the Woolfridge cross-sectional panel data book or the econometrics textbook by William Green. Or then the more specialized textbooks, but a good reading would probably be the How to Do XGA12 paper by David Woodman that explains the XGA12 command. Most of the things also apply to the XGTPD GMM command, which is similar, although a slightly different syntax. At some point, I hope that I can also write a paper myself. So far, I didn't find the time. Most of these more specialized aspects, in particular about the moment selection process that I'm talking about right now, that's really something where you then need to look at the specific research paper here. There was a recent paper by Jan Kiewit. It is not too hard to read, and this might be a quite helpful paper to get some intuition and some ideas about how to deal with these dynamic panel models. It's published last year in the journal called Econometrics and Statistics. But yes, that's something. There's no real textbook that covers all of these more specific aspects, also including curtailing, collapsing. That's often not really covered in textbooks.
Right, and I think that's understandable considering that all of this is still evolving. So,
exactly.
It will take time to, appear in the textbooks, right? Thanks.
Right. Okay, then let's choose model 7 as our new maintained statistical model, where we removed some of the legs, we added some interaction effects, but we still include the time dummies. And let's move on from there. We still treat all of the regresses as endogenous, which is the safest way to do. Although you might, in some cases, get problems with under-identification because when the regressors are endogenous, we need to go further back in time to find instruments, and those instruments could potentially become quite weak. So treating a regressor as predetermined or maybe even strictly exogenous might help us to deal with potential weak identification or under-identification, obviously at the cost that we need to make stronger exogeneity assumptions that may not be justified. So in the next step, we might see whether we can classify some of these regressors as predetermined or even strictly exogenous. We've seen how we can do this with the incremental over-identification test. We can check whether some additional instruments that are only valid, say if a variable is predetermined, whether this additional instrument would be justified based on the incremental over-identification test. And we still keep an eye on all of the other specification tests and the model selection criteria as well. So let's keep our model 7 as the maintained statistical model. And what we haven't done so far, let's look at the under-identification test. And here we see the under-identification test does not reject the null hypothesis of under-identification. So this could indicate a potential problem. And one way to deal with potentially weak identification is to look whether we can find some stronger instruments, for example, for the regressor K and the regressor W. These p-values are still quite high. Then we might maybe try to treat them as predetermined or strictly exogenous to get some stronger identification result here. So what we do first, let's treat W as predetermined, which means in addition to all the legs from 1 to as many as there are, now the contemporaneous value of W under the forward orthogonal deviations also becomes a valid instrument. And I specify this as a separate option. When I specify this as a separate option with the over ID option, then we can check separately the incremental over identification test just for this extra instruments that we are adding here, which will be this group 7 for the forward orthogonal deviations model. We add contemporaneous W as an extra instrument. So next we want to check in the incremental tests whether this extra instrument is valid. So without this extra instruments in the excluding column in row 7, the over identification test passes. So that's good. So we can use this as a baseline. Then we look at the incremental test, the difference when we include this extra instrument. The p-value of 0.3 seems reasonably large. So to justify to include this extra instrument, eventually, we're essentially treating this regressor as predetermined. I skipped some intermediate steps. I'd also check for predeterminateness of the regressor K. And for the interaction terms, the tests will justify this, just believe me for the moment. And then eventually we can also compare our initially maintained statistical model with the improved model to see whether it's really improving in terms of the model and moment selection criteria. And indeed, the new model has throughout smaller values of the model and moment selection criteria. So adding additional moment conditions, additional instruments for the same number of coefficients improves the fit. Looking at the under-identification test, it's still not satisfying. You're still not rejecting the null of under-identification. So maybe treat some of the variables as strictly exogenous, not just predetermined. Here I do it for the regressor K. Previously, I used all the legs from 0 as far as we can for the forward orthogonal deviations model of K as instruments, treating it as predetermined. Now remember, if it's strictly exogenous, based on the idea coming from the fixed effects estimator, we can actually use also the contemporaneous term of K as an instrument for the model in mean deviations, which is what I do here. I specify an additional option. I specify this extra instrument, which is for the model in mean deviations, which is only valid if K is indeed strictly exogenous. Add this extra set of instruments called set 7. We can look again at the incremental over identification test. Excluding this additional instrument, the test is fine, so we can use this as a baseline. And then the incremental test also does not reject the validity of the extra moment, contingency extra instrument. So treating this extra instrument, or this regressor as strictly exogenous, giving rise to this extra instrument, it seems to be absolutely fine. Now looking at the model moment selection criteria, the picture is not that clear. It didn't seem to change much. For the Ikaitia version, actually the previous model would still be preferred for the Bayesian version. Now the new model would be preferred. So that's a bit inconclusive. But what really made a difference here is when we look at the under-identification test. Now treating this regressor as strictly exogenous really helped us in terms of identification. Now we can actually reject the null hypothesis that the model is under-identified. So the trade-off between making a stronger assumption on K that may potentially be invalid versus achieving identification seems to be in favor of treating K as strictly exogenous. Then we can possibly go back and redo some earlier steps, see if we can refine the model a bit more. So this precise sequence is not set in stone. It's just a guideline, more or less. We may want to add some time invariant regressors. Again, that's not necessary to find a good baseline model because we can just subsume them under the unobserved effects. But maybe we are particularly interested in some of these time invariant regressors. Then this might be a step now where we could add them, but keep in mind we specifically need strong instruments specifically for those time invariant regressors if we want them. Now, in terms of efficiency, either or if there are still concerns with under-identification, we might want to add the Planter and Bond instruments for the level model under this additional initial conditions assumption. First of all, of course, we need to think about, is this additional assumption, this mean stationarity assumption, justified? Are the countries or units of observation sufficiently similar to justify this additional assumption? If there's no evidence against that based on theory, then we might add these additional instruments for the level model. We start with checking this for the regressors. I guess I skipped some intermediate steps here. And we might find that some of for two of the regressors W and K, but not for YS, these additional instruments would be potentially justified, given that it's not the case for YS. So not for all of the regressors, I don't add the Lambda bond instruments for the leg-dependent variable, because that would usually require that the mean stationarity assumption is really justified for all of the variables in the model. So I just do it for the regressors W and K. Again, add them as a separate option, which I can then check with the incremental over-identification test. And here, really, there's no concern about these extra instruments for the level model. As an alternative, and really it's an alternative, usually you would not combine the nonlinear moment conditions with the Planter and Bond level moment conditions. You do either one or the other, because typically the Planter Bond instruments would make those nonlinear moment conditions redundant. But if we are not satisfied with including the level moment conditions for sufficiently many variables, then it might be beneficial to instead use the nonlinear moment conditions that don't require this additional mean stationarity assumption. So we just add the NL serial option. You can also check the incremental test for the no serial for the nonlinear moment conditions. And we could do the same again with the nonlinear moment conditions under homoscedasticity to see if we can improve it a bit more. But let's just stick to this here. So this might now be a specification with which we are finally happy, and then could go back to the model and eventually start interpreting our results. So essentially what I've shown here is some way to reduce the arbitrariness of the model specification approach. So you don't really just pick the results you like most, but you really have a clear procedure that you follow that makes it harder to attack your final results eventually. A word of warning still, with this repeated testing that we have done, we obviously run into problems of repeated testings that invalidate essentially the usual p-values. So we need to be a bit more careful in interpreting the p-values and standard errors due to the repeated testing that we have. And to be on the safe side, you don't usually want to stick to, say, significance levels of 5% or maybe 10% as cutoff values, where as soon as you get a p-value in a specification test of 0.101, so you're on one of the side of the cutoffs, you accept this new specification. You really want to be a bit more careful here, maybe only accept a new specification if the p-value is really quite large, say 0.3, 4, maybe 0.5, to minimize the potential problem of accidentally accepting a model that's misspecified. So just stay on the safe side by choosing for the model specification some higher p-values than you would normally do. Also, a few final words. When it comes to curtailing or collapsing, there's no real guidance on what is preferred or not. In some recent Monte Carlo study, a combination of both often performed well. There's no clear guidance that you should always do one or the other. And in some cases, you may not actually want to use the two-step or even iterated Gmm estimator. In particular, if you have a small sample where efficiency doesn't matter too much, you just want to make sure that you avoid any problems with imprecise estimation of the weighting matrix, then maybe play it safe. Stick to the one-step estimator, even though it's not the efficient one. Efficiency is less of a concern if you really have a small sample. And finally, just don't follow any of the procedures too mechanically. Just don't use the default settings mechanically of statistical software packages. Always try to understand what are the assumptions that you make, and then explicitly specify everything according to those assumptions, so you make sure you really get what you want and you're not surprised by some hidden default settings of some of the commands, which in particular with the official data commands, in some cases also with XT12 can bite sometimes, that the commands do something that you're not really aware of if you just follow the defaults. Okay, that basically brings me to the end of this presentation, and I'm happy to answer more questions.
All right, Professor Sebastian, first of all, thank you for sparing so much of time and delivering this lecture with such precision. So the floor is open now for questions. If you have any questions, you can post them in the chat box, and I'll put forward these questions to Professor Sebastian. Any questions, please? Okay, so Monica is asking, when do we use one-step GMM?
Right. The one-step GMM, as I just said, you can, in particular, use if you have a relatively small sample, where it's often problematic to get a reliable estimate of the weighting matrix. You need this weighting matrix, this estimate of the weighting matrix, to get the efficient two-step estimates. But if this weighting matrix is poorly estimated, then we might get very unreliable estimates in our second step. So this can be a problem if you have a small sample size, not in particular, not many cross-sectional observations. If you have a huge microeconomic data sets with thousands or 10,000s of individuals, then that's usually not a concern. You really can go for the most efficient approach, which is doing a two-step. The other situation where a one-step estimator is also the efficient one is where you just have the transformed model, so either the forward orthogonal deviations or the first difference model. No moment conditions for any other model like mean deviations or the level model. And the homoscedasticity assumption is justified. So that's a rare, very rare situation where the one-step estimator is also the efficient one, but most of the time it's not.
All right. So any other questions, anyone? Okay. So meanwhile, I have a couple of questions for you, Professor Sebastian. So
yes.
Could you please go to slide number 36?
Pratik, Ananya has raised hand.
Acha, okay. Sorry, I missed that. Ananya, ma'am, would you like to say something?
Yes, actually, I just written, first of all, Professor Kripfganz, we really appreciate your lecture, the clarity, your coverage. I mean, thank you so much for taking out so much time for us. Now, what I wanted to ask is, as a research student who's planning to work on dynamic panels, what kind of statistical and mathematical prerequisite would you recommend, especially in terms of matrix algebra and, basic statistics?
So in particular, if you want to understand and work on the theoretical econometric aspect, then matrix algebra is something you cannot avoid. You really need to get used to, and it makes your life much, much easier working with matrix notation and being familiar with matrix algebra. So that's something that's really extremely important. And then, of course, all the statistical theory, starting with expectations, variances, diffusion theory, and then in particular asymptotic theory, modes of convergence, consistency, efficiencies. These are all the things that are really important to understand all the details that may not always be necessary if you just want to apply these methods. Then we don't need to really understand each and every detail of the theory. But if you really want to work in that area, then you can't really get around it.
So in particular, could you please suggest, at what level? So for instance, the basic introductory text by Jeffrey Woolridge, it has an appendix on matrix algebra. It has appendices on basic statistics. Would that kind of familiarity with the material at that level be sufficient, or would you suggest some other, textbook that could be indicative of the level at which the competence is required?
Right. So with the material in the appendix of the introductory book by Woolridge, that's definitely a good starting point. It may not be sufficient to understand everything. So if you dig deeper into the material, you might have to use but it get used with some of the extra terminology and notation that's then introduced in the advanced textbook by Jeff Woolfridge, Econometric Analysis of Cross-Section and Panel Data. But before you start with the advanced textbook, I really suggest to be familiar with what he has in the appendix of his introductory textbook. That's really the foundations, that what's necessary, but I don't think it's really sufficient. So if you really want to look deeper into this area, you need to have a bit more in knowledge of advanced techniques as well.
Okay, thank you so much. Thanks a lot.
Okay, so Professor Sebastian, coming back to my question, could you please go ahead to slide number 37? Next, please. So I basically want to discuss the slide in which you introduced two-step GMM along with the command. So I am currently referring to the slide numbers of your London Stata presentation, London Stata conference presentation.
Okay, let me.
So yeah, the slide where you discuss the command for system Gmm Estimator, the XTDPT command.
Okay. This one.
Yeah, this one. Yes, absolutely. So, I just want to confirm my understanding with regard to the syntax of the command. So, Professor Sebastian, we always have two models in the process of dynamic manual estimation. So one is a model, and then one is the level model, and then there is the transformed model. So like in this case, the transformed model is being derived by taking the first difference. So now I want to understand that W and K, these are my independent variables, right? And one being predetermined and another being endogenous, right? So now when I start,
here we treat both as predetermined.
okay, all right. So let us consider them to be predetermined in this case. So now when I open my first GMM bracket, GMM bracket start n dot lag 2 to 4. So now this bracket I'm opening for my lag of the dependent variable. But as you can see, we haven't used the model option in this GMM bracket. So then by default, this model option is level, I suppose.
And no, we have specified this model, the separate model option at the beginning, model diff.
Yeah, absolutely. So which means that we are using the first difference transformation, right?
Right. So this standalone option, model diff, that is setting the default. If I had not specified model diff here, then you were right. Then GMM without a specification of the model would refer to the level. But because I specified the standalone option model diff, I've essentially changed the default. Now the default is model diff. And if I don't specify any sub-option model within the GMM option, then this refers to the new default, which is the difference.
All right. So now since you have used model diff option outside the GMM brackets, it means that it has been set to the first difference transformation by default. So now for the level model, we always use the lags of the first difference equation as our instruments. So when you again open the GMM bracket in the second line of this command, GMM bracket start n, comma lag 1 and then you specify diff again and you use model level. So now diff, I suppose, is referring to the transformation of the instruments here, right?
Exactly. So diff is this delta in front of y t minus 1. Here I use the first difference of y t minus 1 as an instrument. Because this is what diff is saying here.
Right. And so when I say model level here in this particular bracket, does it mean that I am now specifying instruments for the level model?
Yes. So you do exactly what we have here. use the difference of the lag dependent variable as an instrument for the level model. So the error term here is not transformed.
Right. Okay. So, all right. So now then see, by opening this bracket in particular and by specifying in the command that lag 1-to-1 of n have to be used as instruments for the level model, and then again doing the same thing for w and k as well. So we have now told Stata in the command itself to use the lag, the first difference lags for the level model, but then are the brackets in the first line, the GMM brackets, the first two GMM brackets in the first line, there are we specifying the lags for the first difference model to be used as instruments?
Right, so for the first difference model, we use this second to fourth lag
of the level values, right?
of the level values as instruments for the first difference model.
Right. So, now since system GMM is by construction a combination of two equations being solved simultaneously, does it mean that we need to always open these GMM brackets twice for any given endogenous or predetermined variable in the command?
So what you could do, you could combine these two yellow options.
Yeah, but then the lag lengths will have to be the same for them, no?
Then the lag length will be the same. So you could specify L.n, so it directly applies the lag with the familiar data times series lag operator to the dependent variable. Right? So instead of n lag 1, you could also type L.n lag 0. That would be equivalent.
Okay. So if now let us suppose consider a case wherein the second line is completely missing, which means the last two GMM brackets haven't been specified in the command, and the command is only being run with the first two GMM brackets, then what does it imply?
Then we just have the first difference Gmm estimator. We just have
exactly.
Yes.
So which means then in that sense, we are using the Erlano-Bond first difference GMM estimator, where only the first difference equation is being utilized and the level values are being used as instruments.
Yes.
Okay. So then by default, it means that let us suppose, I say I'm not concerned with the number of brackets that I have to open. I'm just trying to get clarity with regard to the fact that for each endogenous or predetermined variable, we need to specifically and explicitly identify instruments for both level as well as the first difference equations, right?
So if you want to have the system Gmm estimator, you need to have separately instruments for the difference and the level model. Yes. So what I think I know where you're coming from. What XT-2 allows you to do, XT-2 allows you to just specify one GMM option, and this will generate your instruments for the first difference equation and for the level equation. That's not what XT-DBT GMM is doing. If you want to have instruments for the first difference and for the level equation, you need to specify separate set instruments. And that's really done on purpose because I always find it so confusing to keep in mind what exactly XT-2 is doing. It's very easy to get confused here, which lags it will produce for which equation, what transformation of the instruments is it doing. So to really make sure that you get what you want, XT-DBT-GMM forces you to explicitly specify everything the way you need.
Right. And Professor Sebastian, let us say if there would have been an exogenous variable as well, let us say M, then for that, how do we open both of these brackets?
So you could just specify another GMM option with lag say 0 to 2. And
Yes.
and for the level model, you would just add it to the second bracket WK and M. So predetermined and strictly exhaustive requests are treated in the same way for the level model. That's no different.
Right. Okay. All right. So, and now with regard to the ending lag length, my question is that is there, is it advisable to use the same ending lag length for all our predetermined or endogenous variables? Because clearly here I can see that you have used 4 as the ending lag length for the lag of the dependent variable, whereas 3 as for W and K being predetermined variables.
So what I've done here is I just have said, okay, I want to use 3 instruments for each variable. So 3 means 2, 3, 4. This gives us 3 instruments, 1, 2, 3. This gives us 3 instruments. And an alternative, equally valid approach would be to say, I always go until the 4th lag. Then you would say, okay, here I go from 2 to 4. Here I go from 1 to 4. This would be totally fine as well. In principle, you could also look at how persistent is a variable. The more persistent a variable is, the weaker the instruments become if you go further back in time. So if you have a very persistent variable, then you might want to use fewer lags than for a variable that's not so extremely persistent. So you could, in principle, also motivate that you choose a different lag order for W than for K, for example. But I wouldn't do it in an arbitrary way, only if you have a good justification.
Right. And this question is coming from the fact that just by playing with the ending lag length, the results can be manipulated quite drastically.
I know. That's why I always suggest decide which lag length you want to use in the first place, and unless there's a severe problem with too few or too many instruments, then just stick to that and try to work with that.
All right. Also, just a quick question. So for the first differenced model, I wanted to understand that, let us say for delta xt, can xt minus 1 in levels be used as instrument? Because for deriving the value of delta xt itself, we subtracted xt minus 1 from xt. So xt minus 1 is being used as an input in order to derive delta xt. So to that extent, can xt minus 1 in levels be used as an instrument for delta xt?
So the idea here is essentially that xt and xt minus 1 have the same correlation structure with alpha I. So if you take the difference, this just nets out. Xit is correlated with alpha I. Xit minus 1 has the same correlation with alpha I. We subtract it, so the correlation just gets netted out. It disappears. So if you just use xit or xit minus 1 in levels, and it's correlated with alpha I, then this will not be a valid instrument. You can only use this if kind of have a random effect assumption where x itself in levels is uncorrelated with alpha I. If you want to make this kind of random effect assumptions, then you can do this.
Okay, so but then the point is that, see, the level values have to be used as instruments for the first differenced values. Then for, let us say, delta xit, should I start my instruments from xt minus 2?
For the level model?
Yeah.
So if there's no serial, pardon me. If there's no serial correlation in the error term, then here there's no reason to start with t minus 2, because xt minus 1 is already uncorrelated with uit.
Okay. Okay. All right. So that's all from my side. There's a question by Kalpita. She's asking in system GMM two-step model, how do we interpret the normality of the error term? How do we address the issue of the error term being normal? Although I understand that this assumption corresponds to OLS, but is there any such constraint in GMM as well?
So normality, being normally distributed, even in the basic linear regression model, that's usually not an assumption we really need. It's not needed.
Absolutely. It is only required for hypothesis testing.
It makes a difference for hypothesis testing. So if the errors are normally distributed, then our test statistics will have a t distribution. So for the t distribution, we need the normality assumption for the error term. But even if the errors are not normally distributed, and that's what we are usually doing, then we can still use the asymptotic normality of the estimator to approximate the finite sample distribution. So whether the errors are actually normally distributed or not might affect a bit the quality of the finite sample testing procedures. But as soon as the sample size is large enough, that's not much of a concern.
All right. So
Pratik, Ankur Bhandari has raised the hand.
Yeah, Ankur, please go ahead if you want to ask any questions.
Hello, Pratik sir. Hello, Sebastian sir. This is actually Dr. Krishna from Helsinki. I joined from my son's computer, so I could not change my name. Sorry for that. Thank you for clarifying so many doubts, and thank you for Pratik for inviting me here. And Professor Gupta was my first great inspiration to get into this modeling. And then now I have been writing a couple of papers on this. My background is from the interface of strategic management and econometrics. So my question is, now these two domains are actually pretty separated, because most of the things that is happening in econometrics, that is actually doing like the contribution like you have done is famous and popular and everybody is in, and we are in that kind of traction. So in strategic toolkit to influence the what kind of plans do you have, and if there is a possibility I can contribute to that?
I'm afraid the connection was not good enough to really understand.
In short, it is how do we make these modelings, these econometrics modelings, very pervasive into social science research?
I mean, these models are not, and these estimation procedures, these are not specific to, say, economics or any subfield of economics, but you could use them to any field you want to. And they are well established in the economics literature, and in particular management science often draws from methods that are heavily used in economics. So I don't think there's any acceptance problem in these other fields if these methods are used there. Particularly if you can, in your paper, then justify why you need to use the Gmm estimator, simply because, for example, the fixed effects estimator is biased in small samples for dynamic panel models. You may have to account for heterogeneity of additional regressors. And then you can reference the existing econometric literature, and that should usually be very fine.
Okay, I think it's time to wind up.
Yeah, absolutely. So Professor Sebastian has indeed once again delivered a
Wonderful
brilliant
lecture.
lecture.
Yes, yes. And we
Right.
are really thankful to you for being with us this and sparing almost 3 hours, more than 3 hours continuously. I mean, we can imagine your stamina. Good thing. Good job. Surinder, can you propose vote of thanks?
Yes, sir. Thanks for this opportunity. I, for foremost and first thanks go to our Professor Sebastian, not only for delivering a talk on very important topic for researchers completely, comprehensively. In fact, it was glass full, virtually brimming. In fact, I would like to add and say that the lecture got converted into kind of a tutorial, and we had much intensive discussion on the subject. So in fact, we had multiple formats delivered in one lecture, and in between in the chats many suggestions have come for further collaborations with you by our people in the department, professors. I'm sure for that somebody from our side will get in touch with you uh, separately. Secondly, I would also like to thank Professor C.P. Gupta for providing me this opportunity. And I would like to also mention, not only for this opportunity to thank, but also the opportunity to our institution to collaborate in this exercise to provide the necessary network infrastructure. Uh, I think that's from my side.
All right. So I think we are good to close today's session. And once again, a heartfelt thanks to Professor Sebastian for taking out time and taking all our queries.
And let me
And
say,
finally, I will say namaskar.
Yeah. Yeah, Professor Sebastian, you want to say something?
yes, let me thank you all again for joining, and in the first place for inviting me. It was a very nice opportunity. I'm glad that I could help with some of your queries, that you were getting something out of this talk. So thank you very much again.
Okay, great. So C.P. Gupta sir, should we end the session?
You can only say namaskar to him and thank you very much.
Right. So namaskar from India, Professor Sebastian. This is how we pay our gratitude to people who help us. So thank you so much for all your support and cooperation and for sharing your knowledge and expertise with us today. Thanks a lot.
Thank you.
And we really hope to have you again in the future. So maybe I'll get in touch with you for sessions in the future.
Good. I'm sure I will stay in touch with you also on this data forum.
Yeah, absolutely. Stata List is our all-time favorite platform to get in touch. Yes, absolutely.
Let's close it, right?
Yeah, absolutely. And thank you so much to all the participants for joining in and for all your queries. Thanks to Professor C.P. Gupta, Ananya ma'am, and Professor Surendra Kumar as well. So thanks everyone. So we will close off today's session. Thanks a lot.